Good morning. It is an honor and pleasure to be again here on this conference. I've known Professor Mastarakis for almost 20 years, and after last few years when the whole world stopped, now we are back in these conferences, and I hope that we will continue as successfully as it was before. My name is Milan Tuba, and my primary affiliation is Singidunum University in Belgrade, but I have other affiliations, and as you can see, I divide my time about 1/2 in Texas, where my daughter is professor, and one part in Serbia, and also I'm visiting professor and have keynote speeches in countries in the East, India, mostly China, and so on. So I'm coming now from India and going back to India on Wednesday, and I'm glad to be here in Athens again. So I will give a much longer introduction about the context of this paper, and it will actually answer many of the questions from the previous sessions. How can this new artificial intelligence technology be used for different problems? This paper is mostly about convolutional neural networks, but in general the area is artificial intelligence, deep learning, and there are other sub-areas. And what is important to understand is that there is really a revolutionary development in this area. In general, in science, we have linear progress, especially in other sciences. There are no revolutions in, I don't know, agriculture, car production, and things like that. Even from some time to time, let's say penicillin was revolutionary in medicine, but it happens very rarely. In computer science, there are quite a few of revolution, and some older people remember invention of PC or internet or smartphone. These things really changed the whole world, not only the research in incremental way. And right now there is a revolution in this application, convolutional neural networks, but somehow it's maybe not enough announced yet because the world was preoccupied with other problems last couple of years. ChatGPT introduced some kind of shock waves, positive, negative, but it really made many people aware that something very important is happening in that area. For ordinary people, also it is visible. For example, unlocking the phone by fingerprint or face recognition was really science fiction maybe 10 years ago. Now it's on the cheapest phone, just something that people around the world don't even pay attention anymore. And some things like, for example, autonomous vehicles. Also, they are driving on the regular roads for a couple of years very successfully, and that was also science fiction only maybe 10 years ago. So the best example to show how this technology is revolutionary is a well-known benchmark problem today. It doesn't work with these arrows.
It works with the mouse.
Yeah, but it works too fast. So I skip, okay. So about 30 years ago, there was an interesting practical problem of recognizing handwritten digits. It was interesting for post offices for sorting mail because people write zip code on the envelope by their hand, and then to automatically sort mail, you need to recognize that zip code. Also in banks, people write checks with their hand, and to sort these checks automatically, it was interesting. Of course, before that, it was license plate recognition, but it is an easier problem because license plates are very regular. Now, handwritten is something that is challenging for the computer, and as a practical problem, that was solved at that time. So there were systems that were in practical use, so it was not interesting anymore in that sense, but a large database was created of handwritten digits. It is at the University of California at Irvine. It's called MNIST database. And for 30 years, it's used as benchmark. So in this area, anybody who is developing new algorithm, new approach, new technique in some kind of image recognition is using that database as a benchmark to compare the new algorithm with old approaches. And in that sense, it is still very important and it's easy to compare how the progress is made. And there we can see that for many decades, we had a regular, linear, incremental improvement. So maybe 20, 15 years ago, we needed a large team of qualified researchers. They spent a couple of months, they develop a new method, and they improve results. And then we can see that accuracy of the recognition can go, let's say, from 98.7 to 98.9 to 99.0, 99.1, and so on. So for years, it was going slowly with huge effort. What we have today is that we have so powerful tools that it is a practice today in any undergraduate class of artificial intelligence. With students in one lecture, maybe 90 minutes, we can develop a model that will have accuracy better than 99%. So what was a huge research effort maybe 15 years ago, now undergraduate student can do in a couple of minutes. Again, let's not get very good opinion about undergraduate students because the tools are powerful. When we say they developed a model, it's actually the tools are so powerful that it can be done maybe in two statements. In one statement, you can say, bring me the database from somewhere in the internet. And in the second statement, you can say, classify those images, and then you get result. So it's not really a huge effort. It is the tools are powerful. And that shows how revolutionary it really is. It's extremely powerful. It's not comparable to anything we had before. Now, how it works. The basic problem is a classification problem, which is a very simple problem, and it does not look so powerful. Classification problem, by its basic definition, is for a set of entities. It can be anything. It can be humans, cars, research papers, whatever. Set of some entities with some properties. Based on those properties, we need to make classification. Which of those individuals belong to a certain class and which don't. So this digital image classification, of course, is that class. In the binary case, we ask a question, is it digit 3 or not? Is it digit 7 or not? And then by combining a number of such questions, we can finally decide this is digit 5, this is digit 7, and so on. So it doesn't look very powerful. And then the basic thing that is used for autonomous vehicles, self-driving car, is the same thing. And it looks very far. Actually, what do we have in self-driving car? The mechanical part of steering, accelerating, braking, that is for mechanical engineers very easy problem. It was solved decades ago, so that's not really, it looks impressive, but it's not worth mentioning in a research sense. So what we have is really, we have a number of sensors. Usually these are cameras. You can have front camera, a side camera, back camera. It can be regular light, RGB, or it can be infrared, or it can be ultraviolet, or any kind of other sensor. And then we do recording. We get continuous images. And then we slice them in static images. And then in those images, what do we need to do? We have a digital image. And then on that image, that digital image, we have to do classification. Is there a stop sign in this image? Is there a pedestrian in this image? Is there some kind of middle line in that image? And based on that classification, then we decide, should we brake, should we accelerate, should we steer left, and so on. So the basic technology that is driving a car without a driver is a classification problem. Complex classification problem done in real time, many times every second for many sensors, but it is the same problem as digital image classification. It is a classification problem. So everything is based on that. And now the problem is, here is an example of some of those handwritten images. And here is how the classification accuracy increased when convolutional neural networks were introduced. And for the classification, what we need is features. Again, for decades, the problem of the features was a very complicated problem, because for each particular problem, we need to determine which features are relevant. We need a small set of features because then it's easier to work with them. And for example, if we need some medical diagnostic system, old-fashioned physician, very old, 200 years ago, would simply look at the people. We have entities, these are people, 50 people, for example, and now we look for the features. We can say, what is your shoe size? But it doesn't look relevant. What is your grandmother's name? But it doesn't look relevant. So he say, okay, let me see your tongue, let me see your nails, let me see your skin, let me touch you here, let me touch you here, let me listen to your heart. And he selects something like 10, 20 features that look relevant for that problem, and he will make diagnosis. Now we can imagine that a technology can develop where we introduce new features. And now let's say we have blood works. So you go to the lab, and from the lab and your blood, they get you a paper with all the parameters. Now you have the same situation, same patients, they are standing there, but they have a piece of paper. For old-fashioned physician, it doesn't mean anything. He's still looking at the skin, tongue, and so on. But the new physician that knows about new features can do even in the dark. He doesn't need to look at the tongue and nails and things like that. He looks at the paper, and then he reads certain parameters, and he makes much better diagnosis, more precise, more accurate diagnosis based on those features that we didn't have before. Then again, here is all the problem starting. What happens if two people mix those papers? It will be a terrible mistake. You cannot mix your skin or your eyes with somebody else. So when physician looks at you, he's looking at you. But if you have a paper with lab results, they can mix. And then he can send to operation a wrong person. So if errors happen, they can be very unpleasant because it is more powerful, but the errors are different because features are different. And the whole story now is about these features. What convolutional neural networks introduce is extremely powerful and also dangerous. It releases us from worrying about features. Convolutional neural networks can take any information that you have and will make features that we cannot imagine. So any problem solved with convolutional problem, it can be a railway problem or any other problem, the convolutional network can say, give me everything. So your shoe size, give me the shoe size. It looks irrelevant, but who knows, maybe there is something. Maybe if shoe is large, the person is large, maybe large people have more problem of certain kind of heart, kidney, whatever. Your grandmother name looks irrelevant, but maybe it can tell something about your ethnic origin, and then some groups of people can be more suspicious to certain disease. It's really difficult to say in advance that any feature is completely irrelevant. We just look at those that are more relevant because we have problems dealing with many features. Convolutional neural networks don't have that. They can deal with millions of features. So they say, give me all the information, and there is a lot of information about everything. And of course, for images, we just take the whole image. We don't try to select, like with X-rays, with ultrasound, look where there is a contrast, look where there are some texture changes and so on. No, just give me the whole image. I don't care about any pre-processing or something. So it's very easy. And now convolutional neural network, of course, it requires a huge amount of data, and it requires a huge amount of computational power. But then it will automatically generate millions of features, select those that may be relevant, and make a classification better than humans can do. So it can drive a car better than humans. It can make medical diagnosis better than humans. And that is good. But Those decisions are based on millions of features that we cannot in our life invent names for them. And the problem is when we want to explain how that diagnosis is made, we cannot. Because it's made on million features, we don't know what those features are. It's not red blood cells, it's not this, it's not that, it's something of those million features. And then when error happens, we cannot explain why that happened. And the errors can be very strange. As I mentioned before, if two people just mix the lab results, it will be terrible. And here there are some well-known examples. For example, that if you have a system for classifying images, and it's a very good system. So you have a large database of images, you have bookshelves, parrots, pandas, monkeys, whatever. And the system is trained and it is excellent. It's doing classification better than humans. If you apply certain amount of noise, like in the middle, which will not change the image for the human, it's the same image as far as we are concerned, the artificial intelligence system will be completely full because it is attacking exactly the feature that it is using for detection, and it will classify parrot as bookcase. As 100%, this is bookcase, I am sure this is bookcase. Say, how is it bookcase? It's a parrot. It was parrot before, and now with this small noise, it didn't change. Why is that happening? Because it is working completely differently. And the problem is, it is powerful because it is working differently, but it may be dangerous because it's working differently because we don't understand it. So if humans are at, let's say, accurate 99%, this system is accurate 99.9. So humans make error 1 in 100, this system will make 1 in 1,000. But when it makes errors, it will look terrible to us because the humans will misdiagnose kidney disease. This system will 1 in 1,000 instead of kidney do operation on the knee. And then we are in very bad mood because that cannot happen. So these are dangers of those systems, but also power of that system. And then, of course, the problem is that these convolutional neural networks have to be optimized. But even without optimization, they give good results. So what is good? You can apply it to any problem. You can take any paper from the literature that is 10 years old or maybe 5, 6 years old. You can apply this method, you can be pretty sure that you can improve results with not too much effort. Just put all the data inside, have some experience with constructing some neural network, and in the first attempt it will improve the previous result because the tools are extremely powerful. It's like, you were digging before with some kind of spoon and now you have a machine. You don't have to be very experienced, you don't have to be excellent. With machine, you will do certainly better than with a spoon. So the paper finally that I wanted to mention today is about satire detection. That is interesting, like in the previous talk, that if you are looking at some texts, you want to understand automatically what it is about. And then what is the problem? That sometimes you have sarcasm. Something is said like, you are very young, but doesn't mean that it's just the opposite. And how can you detect that? And now it's not even in the text, it is in the image. So it is a picture of something, and then, something in that image is really sarcastic. How can you do it? Well, you simply collect the database of such images, you do annotation for some training set, and say, this is satire, this is satire, this is satire, and then you create a network, you train the network, and it will do a decent classification. So we had a recent paper where these people mentioned here made some network and they created a database with some number of images. You have the data here, and they made some classification. In such situations, of course, it is initial work, so classification is not 99%, it is more, the area is more difficult, and they had some results. So what we did as a first step, we created a different neural network with some experience. This is, you decide about the parameters, how many layers, what type of learning algorithm, what type of, how many neurons in each network, and so on. So with some experience, but this is really called guesstimate. We don't have scientific method how to construct network. The good thing is whatever you do, it will give some acceptable results. The more complicated question is how to improve it. So with experience, we played a little bit with some parameters and we created a network that is simpler than the previous network. It has smaller number of layers and increase the accuracy. So that is basically what you do in the research. That is now incremental improvement using these tools, not against anything else. If you use it against any old method, you can certainly improve it a lot. But if you compare it to some previous convolutional network, then of course you cannot improve it so significantly, but you still have a wide area where you can improve it. So here are examples of some of the images where there is a cat, feed me slave. It is some kind of advertisement, and of course human is not slave to cat, but the automatic system cannot know. It simply recognizes the letters, translates them, and so on. So these are few examples from the database. The network was trained on those examples. And here is a description of the network that they used with number of layers and so on. And here is a network that we made a little bit simpler with 2 layers less than the previous network. So it should also translate to less computational time for training the network. And then, of course, we did some initial optimization, but very coarse. With grid search, we try a couple of values here and there. We make a matrix, let's say 3 by 3, and then we try those 9 values and see where the results improve. That is a very, very crude method. Often people don't do even that. But with some crude optimization, we were able to improve results where some pre-trained network and some previous literature had accuracy 67, 68, 73. In that paper that we refer to, they had 84. We improved to 88. And that is typical for that area, that with some experience and playing with the network architecture, you can get that type of improvement. Now, what is left is the real research, and that is the continuation of this paper, and that is optimizing these parameters, not by crude grid search, but using swarm intelligence algorithms, which can really improve a lot, but then it requires huge amount of time. And the problem is that here computing the objective function value is really training the network. These algorithms usually expect that they can do thousands in a second. Here you may need minutes for one value, so it is very, very different, and then you have to make adjustments. But we did a number of papers in that area before. So here is some list you see in optimizing those networks. So you see in quite a few cases it was successful. So we have no doubt that here we already made some improvement, and in the future with this method that we applied before, with more effort, of course, it can be further improved. And finally, for younger researchers, that is excellent research area. Convolutional neural networks is extremely powerful. It doesn't matter what you do. You can do a railroad oscillation, you can do floods, you can do crop control from the satellite, crop diseases, anything. There are images or some kind of parameters. If you use convolutional neural network as a hammer, you hit it hard and you will improve results. And that is good because you cannot waste 3 years and finally see that it was a dead end and try to something else. Here, the success is practically guaranteed. So, thank you. That's all.